All right, let me start setting up things. So entire screen, share. Um, so can folks see my screen? Yes.
Yes.
Cool. All right. So this is a continuation of chapter 5. Previously, we did some basics of machine learning. This is the machine learning chapter, by the way. So we did some like kind of why machine learning kind of things, right? And very basic ideas about what machine learning was. And then there was a case study where we did linear regression, and basically kind of derived linear regression and kind of see. So here we're going to start talking about capacity overfitting and underfitting. So one point that um, you know so last time when we did linear regression, the focus was on learning from the training data, right? So the point that the author makes here is any errors that arise from the predictions of this model on the training data, right, on the actual labels of the training data. That's called the training error. And when this model is applied on unseen data, which was not used for training, um, on a test set, say, so that would be called the test error or the generalization error. One other thing, or the main point here is that, you know, if you are just training, right, um, and you are trying to reduce the training error in training, you are basically doing an optimization problem. It is not really machine learning. So when you think of machine learning, you want this model to also minimize the test error or the generalization error, right? So the model has to be generalizable to data that it was not trained on, right? But which is in the similar um, kind of data distribution, similar data distribution. So so that's where the idea of the generalization error comes up, and so essentially here, if you go back to the linear regression model, you basically trained on the it's basically the L2 norm here, which is the sum of the difference between the predictions and the labels, the square of that and square root of the sum of that, right? So here, the actual when you train the model with the training weights X train, with the training inputs X train and the learned weights W. So this produces on the data. This would produce the predictions, right? Y hat equals XW here. So this is how you basically talk about this equation. You do the square root of the sum of the squares, and then you divide by the number of training examples, right? And so this is the training error. But in ML, the main idea is that if your test error is small, and that's the only difference is that M train and M test get interchanged, and X train and X test get interchanged, right? And yeah, so this is the test version of that. Okay. And then it says, okay, so one of the other things that they talk about is the idea of IID, that is identical. Wait, so what is that called? Independent and identically distributed, right? That's the term. So the definition here is that each example in the training or the test data set, whatever data set the samples were drawn from, they are independent from each other, that they don't have dependencies across data elements, and the training and the test set are identically distributed. So generally, if you do like a stratified sampling, or you know or random sampling is even better, but sometimes if your data set is very unbalanced, you would prefer stratified sampling, where you try to keep the mix of the classes the same. So even so, in general, those are kind of they're theoretically not identically distributed, but they're kind of works well enough, right? So and then so in okay, so it says here, in the ideal world, the training error is equal to the test error, because it has been the data is drawn from the same sample, so ideally they should be the same. However, in general, because you trained your model on this training set, and the test set is not the same as your training set, your test error usually is higher than your training error, right? Um, so yeah. So then they go off to the point where let's see. Okay, making training error small. Okay, so then this is where they go and talk about, based on what we just discussed, they discuss underfitting and overfitting in that context, right? So in case your you know the training, so the idea is that you have to make your training error small and your test error small, right? So if your training error is small, but so during your training, if you cannot make your training error small, then it typically is a case of underfitting, right? So you haven't been able to fit your data to your training data, your model to the training data, right? Well enough. And in case where there is a gap between the training and the test, but the training error is small, but the test error is, there is a gap between the two. That is, and when you cannot do that, it's a case of overfitting, right? So that's the idea here with, and so then this leads into the idea of capacity, where so if the capacity is low, so when you think of a model, how capable it is, right? So if you're and you call it capacity. So if your capacity is low, then this would typically lead to underfitting, and if your capacity is high, it is it'll too high, it will lead to overfitting, right? So you need to have this Goldilocks thing where it's just right, right? So then they give you some examples here, where examples of capacity, where they talk about linear regression as an example again. And but unlike traditional linear regression, where you have y equals wx plus b or b plus wx, they also start adding quadratic and other polynomial features, right? So as you add these additional quadratic and polynomial features, your capacity tends to increase, because assuming your data is nonlinear, it would tend to fit better, right? But so but this is also like it's again, there is a case of like too little and too much, right? So in this example here, you see that these points are your data points, and you're trying to fit a linear model. So this is fitting, but it's actually giving you quite a lot of errors, right? So you can see, if you can kind of focus out a little bit, you'll see that it looks like a parabola, right? The points. So in this case, quadratic is the best fit. So, and you can see that it fits very nicely. However, you can fit it even with a higher order polynomial. I think in this case it's a ninth order polynomial, so x to the power 9, or x to the power 8 or 9, whatever. So and you see it fits very well. But if you take the same model and you run it against test data, and assuming that the test data is also quadratic, it will not fit as well, right? So this is a case of overfitting. And so that is one example of capacity. There is also other capacity where you're talking about representation capacity, right? So if you have a model, and like a neural network model, for example, and you have, like, say, x number of layers. So those layers would translate into the number of weights, right? So how many layers, what are the input and output sizes, and so forth. So they'll have transformation matrices at each end. And so the number of parameters that the weights imply is is a gives you an idea of the representational capacity of the model, right? So there is also another definition of capacity, where called the Vapnik-Cherovansky dimension, or the VC dimension, which is another measure of model complexity or capacity, which you know they throw this in. I don't see it, like, it's just a name here. It doesn't actually give you any, they don't go deeper into this. So And so again, this reiterates this whole thing. The most important results in statistical learning theory show that the discrepancy between training and generalization error is bounded from above by capacity. So this is where the VC dimension idea comes in, by a quantity that grows as the model capacity grows, but shrinks as the number of training examples increases. So basically, they are talking about the the one point of error is this is the bias, right? So so as your bias, so this brings in the idea of bias and variance actually. So if you look at the last bit, it says the but shrinks as the number of training examples increase. So the error, the training, the discrepancy between the training and or the even the test error, sorry, the test error or the generalization error, that shrinks as the number of training examples increases. This is an example of bias, right? So decreasing bias. So as you see more examples, you see more, you have seen more areas of the the space of the data, right? So and that gives your model more rounded view of the thing. So the bias of the model goes down. On the other hand, if you look at it says this training and generalization is bounded from above by a quantity that grows as the model capacity grows. So there is a limit, upper limit to how much this error can grow as the model capacity grows. So that gives that asymptote, right, basically gives you an idea of what the model capacity is, right? The limit of the model capacity, which is the kind of the VC dimension here. Let's see here. Gaps, go to the model capacity. Yeah. So this is where I kind of pointed out, the gap between the training error and test error grows as the model capacity grows, and this is the variance, but shrinks as the number of training example increases. This is the bias, right? And we will see bias and variance in lower, further down. So then they also talk about, so far linear regression and this kind of neural networks even, these are basically parametric models because they are governed by the number of parameters. Their capacity is governed by the number of parameters. There is also another class of models which are non-parametric models. One example they have given is the nearest neighbor regression algorithm, where basically to find, so if you're given a test example, you try to find the nearest neighbor in your training set, and that is the prediction you give back, right? But that doesn't depend on the number of parameters. Another example is like text-based, like lexical search kind of things, right? So those don't actually have any relation. They have parameters, but the number of parameters are not, they don't govern capacity, right? So they are called non-parametric models. And it says here, so then they go into a idea of and here is another little point that you can wrap a parametric model within a non-parametric model. So for example, if based on the input you route it to different models, right? The most efficient model for that input, that would be an example of a non-parametric model, right? Wrapping parametric models. And you can go the other direction as well. So then they talk about this ideal model, which is an oracle, and which would, which knows the true probability distribution. It doesn't know the answer to your test data, but it knows enough about the training data so it can actually, infer things from the true probability distribution that generated the training data. And however, even that model can make errors because your test data can be, outside theoretically, or there could be noise in your test data which it would not be able to predict, right? So that error between the oracle's predictions and the true distribution, that is called the Bayes error. So again, it's a factoid that the authors throw out, and figure 5.4. So here they actually talk about all these things. So where they talked about this upper limit and so on, right? So if you can see here, so this is a training data set that they kind of created or they created a bunch of synthetic data of different sizes, and then they plotted the generalization error, I think, capacity. Yeah. So and on the y-axis, yeah, on the y-axis they plotted the error that the model got during training. So as you can see here, for a quadratic model, and this model was a degree 5 polynomial. So essentially the real data distribution is like a fifth order polynomial, and they tried to train a quadratic on it. So this, you can see it's asymptoting with at the base error level, right? And because the test, the quadratic test is actually underfit, it's not as good, because it should really be a fifth order polynomial, but it's actually just a second order, right? So the test error is actually higher than your base error. And then if you look at the optimal capacity for the test, the red line, it actually approaches the base error, right? So this is the lowest it can get, and it's almost closest to this. Also, if you notice, so again, this time they plotted the degree against the data set, and as you can see, even when you are overfitting, right? So as you go increase the degree, it kind of plateaus at you start getting lower errors. However, the best errors that you got is around this area, which is around 10, between 10 to the power 1 and so 10 and 100, right? Samples, and you can see it has the best it plateaus at this capacity, right, at the fifth order polynomial. So which is basically what you would expect, right? So yeah. And again, so the next section is basically talks about the no free lunch theorem. So essentially, it's all it says is that there is no one algorithm for all data models, and that given a data set, you need to or given a task and a data set, you need to customize things, right? For so the need for model training, basically. Okay. So yeah, averaged over all possible data generate. So this is the free lunch theorem. So it states that averaged over all possible data generating distributions, every classification algorithm has the same error rate when classifying previously unobserved points. So in other words, in some sense, no machine learning algorithm is universally any better than any other. So that is like a very general statement, but but that is not true, right? I mean, you have machine learning models which are good for specific tasks and specific data points. So that's where they're saying, if you make assumptions about the kind of probability distributions we encounter in real world applications, then we can design learning algorithms that perform well on these distributions. If you think in terms of neural networks, it's more it's not really true. Even this one, it's but in traditional machine learning algorithms, yes, it does help to know a little bit about the data distribution and see if at least it is like quadratic or what order polynomial would best fit it. But yeah, so that's basically the free lunch theorem. So next we go off to regularization, and so the idea here about regularization is to give the algorithm preference for one kind of solution over another, right? So one of the approaches for regularization is weight decay, where you essentially say that I want all my weights to be as small as possible, right? So that way, no one weight will push your solution, one way or another. So it doesn't have undue influence on the final result, and that is one way to prevent overfitting, because you don't want to trigger off. So assuming that you had very peaky weights for some sort of model, and then you got a training or a test example where one of those weights get triggered like really heavily, so it becomes like an anomaly, right? So the idea here is that to combat that, you want to keep your weights like really small, and so that is the weight decay regularization that is used in a lot of neural network models, and even like linear regression or other traditional models. So so that is you might have heard of L1, L2 L1, L2 regularization and so forth. So that's basically weight decay, right? And then let's see what the, so again, it's the same idea here that we talked about earlier, where looked at the polynomial case, but you can achieve the same similar kind of results with weight decay as well. So as you can see here, this is the same data points that we saw, and we know it's quadratic. However, they are trying to fit like a linear. So here I think it's a linear model, but yeah. So yeah, it's a linear model with a, yeah. So it looks like where is this? So essentially, you have this. So how do you implement the weight decay, right? So in your cost function, so your cost function is the whatever loss function you have, right? The mean squared error in this case on the training set, plus a term which is like this is the L2 norm, where you basically multiply the weight by itself, so weight squared, and you have like a like it's a parameter, it's a hyperparameter in this case, which governs as to how important this regularization is to the cost function, right? So when the lambda is 0, then there is no regularization, right? And then the larger the lambda, the more the weights are forced to become smaller, because you're saying that I want, this is part of my cost, right? So I want this to go down as far as possible. So I don't see the, but so basically that is your thing. So using that sort of cost function, if you had like a very high lambda where you are regularizing very heavily, then it almost becomes a straight line. So you basically get like a linear model, right? Actually, it'll be, yeah, okay. And so this is actually not a linear model. This is a polynomial model, I think, because you're so degree 9 polynomial, I think it is. So because you're forcing you're forcing the weights to become very small in this with a high lambda, it's almost like a straight line. Then with a medium, again the Goldilocks thing, right? So it kind of approximates. It's not truly quadratic, but it kind of approximates the point. And when you have very low lambda, where the regularization is almost absent, it goes back into this old, the degree 9 polynomial, very wiggly kind of thing, right? So, and this is overfitting, this is underfitting, right? And so essentially, regularization is another way to implement this, to combat overfitting and underfitting. And so the way the regularization works is that you add the regularization penalty to the cost function. We already saw that here in equation 5.18. And so again, he talks about the philosophy of, so again here, right? The no free lunch theorem has made it clear that there is no best machine learning algorithm, and in particular, no best form of regularization either. Instead, we must choose a form of regularization that is well suited to the particular task we want to solve. So here they kind of highlight the importance of regularization. And the philosophy of deep learning in general, and in this book, is that the wide range of tasks, such as all intellectual tasks that people can do, may be all solved efficiently using very general purpose forms of regularization, right? So, so he kind of boosts regularization here as a very important thing to think about. The next piece is about hyperparameters and validation sets. So one thing that we have been talking about, parameters, right, of the model. So the parameters are the weights of the model, and the hyperparameters are things like the lambda that we just saw, the regularization coefficient, right? So one thing that is distinguishable is that hyperparameters are chosen by the researcher or whoever is building the model. They are not learned, right? They are chosen, right? They are selected from a set. So when you have to do a grid search or a random search for hyperparameters, you're essentially selecting specific hyperparameters. You're not learning them, right? So that is one big distinction between hyperparameters and parameters. And these hyperparameters are the settings that control algorithms' behavior. such as the weight decay coefficient, degree of polynomial could also be a hyperparameter. So how to select those hyperparameters, right? So that is another big question. So so we have already talked about the training set and the test sets splits. However, the one issue with test sets is that it happens at the end, right? So once you cannot you cannot look at the test set until while you are training. That would be making overfitting to the test set, right? So but so while you're learning, you have no idea of whether your model is going to be any good or not, right? Or it's going to be good on the training set, but you don't know how it will perform in real life. So so that is piece of optimization. But you also want to know how these other parameters, the hyperparameters that you are choosing, how they are going to affect the training, right? How they're going to affect their final model. So for that, you need a validation set that you basically split out of the training set, and during training or during different training different models with different hyperparameters, you use the validation set to decide which set of hyperparameters is the best fit for the model, right? So your validation set can be it has to be split from the training set and not from the test set. It is used to make choices about hyperparameters. It is and of course the rest of the training set is used to learn model parameters. And in general, validation error is generally less than the test error, but probably greater than the training error, right? So there is an observation about stale benchmark. Okay, yeah. So it says, so here is another observation that for well-known data sets, because so many researchers are constantly hitting that data set to create models and trying to publish state-of-the-art benchmarks, there is the danger of leakage, or so it says here, in practice, when the same test has been used repeatedly to evaluate performance of different algorithms over many years, especially if you consider all the attempts from the scientific community at beating the reported state of the art. So you're basically looking at the test set, right? On the test set, we end up having optimistic evaluations on the test set as well. So there is, if you don't change your benchmarks, it can lead to some sort of data leakage along these lines. And the next thing is, how do you how do you use validation sets in this case, right? And especially because data sets cannot, if you have large data sets, then you don't need to think about cross validation. But if your data sets are small, then you want to make the most efficient use of data. So cross validation is a nice way to do it, where you trade compute for the lack of data, right? So the idea is that you, in k-fold cross validation, you split your training data into k pieces, and then you train on k-1 data sets, and you validate on the last one, and you keep rotating through this splits, right? So first you do, maybe if it's 5-fold cross validation, first you do 1, 2, 3, 4 for training, 5th for testing, then you go down in 2, 3, 4, 5 for training, 1 for testing, and so forth, right? And you keep rotating, and then you take the average of the validation errors, and that is your validation error using cross validation. The next piece is estimators, bias, and variance. So the first, so we kind of referred to bias and variance earlier, but let's go deeper into this now. So foundation concepts used. Okay, so first off, he says, why should you talk about this, right? I mean, it says foundational concepts such as this are useful to formally characterize notions of generalization. So bias and variance are actually related to underfitting and overfitting, as you can see here. So the first point is that he talks about is point estimates, where it's a single best prediction of some interesting quantity. So so it can be like a single parameter. So if you have a data set and you say, okay, the mean is the best estimator, it's a single parameter. It can be a vector of parameters. Again, by the same token, you can describe a data set with its 5 common statistics, the median, mean, mode, first and third quartile, and so forth, right? So you can set a vector of numbers, or you can even describe it as a function. Like you can say that this data set approximates a normal function, or a Bernoulli function, or whatever, right? And they make the point here that the function estimate, where is this? There is so there is a point here they make that the function estimate is basically a point estimate in function space, right? So I thought that was quite interesting. I think this is where not predictable. We'll come to that. Okay. So where is this? Maybe it's somewhere here. Okay. I think he talks about it in the context of where it does supervised learning. It's probably further down. Okay. So there are some examples of estimators like, Bernoulli, you can approximate the Bernoulli distribution using the probability, the p value, right? You can approximate a Gaussian by the mean and also by the variance. So and the definition of bias is that it is the expectation of the the model parameters, the learned parameters, minus the actual actual parameters. That is the bias here. And so they give you an example here. So if you look at a set of samples, m samples, which are IID according to Bernoulli distribution with mean of theta, then you can basically describe the probability distribution as this. We already learned this in the statistics chapter. And so the common estimator for the theta parameter is the mean of the training samples, right? So that is the estimator, the point estimator we talked about earlier. And so this is defined as just the mean of the training samples. And so how do you calculate bias, right? So you already know from this, where is this? From 520, right? That it is the expectation of the learned parameters versus the actual parameter. So the expectation of the learned parameters is basically just, we already know from here, right, that this is the expectation. Now you can take the, you can take the 1 by m out of the summation because it's, or out of the expectation, and you just use this. And this, I mean, I was able to do a shortcut here. I mean, this is obviously, I'm not able to basically capture what, how this translates into this, right? Sorry, how this translates into this. But you can also think about this thing, the e to the, or expectation of x in a Bernoulli case is the actual, the probability, right? So that is a known formula. So you can jump down, you can skip this and basically say that, 1 over m, it is the summation of the mean, the p value of the Bernoulli. And then, because this is basically just m theta, so it cancels out as theta minus theta is 0. So the bias here that you calculated is 0. So this is known as an unbiased. So you're basically saying that the bias of a Bernoulli distribution can be effectively proven to be 0, right? Similarly, if you look at the Gaussian distribution, again, the point estimator that you're talking about is the sample mean. So again, if you go to calculate the bias using 5.20, right? So where is this 5.20? Here. So it's expectation of the learned estimator versus the model estimator. You can just substitute here, right? And sorry, you can just substitute here using this the sample mean, right? And then if you you can take the 1 by m out and you can put the estimate, turn it into a summation of the expectations, and that gives you like 1 over mu, sum over m terms mu times, right? So it's m mu minus mu, so mu minus mu is 0 again. So again, the mean of the Gaussian is also like unbiased, right? However, it is not true for the variance of the Gaussian. So if you do the variance, I wasn't able to figure out how this came about, but this is the sample variance is again, like just like you have created a point estimator here. Here is also like you can have a, for the variance you can have a sample variance, which this is also quite understandable, right? And then so the bias in this case would be the expectation of this quantity minus the actual variance. Um, this one I'm not able to derive. So I tried, I wasn't able to. But then this leads to this,
It's funny. I have the same exact comment on my book. Not sure where the m minus one comes from. I
yeah.
wrote the same on the book.
Oh, that is the point you made in the Slack.
No, no, no. And on
Okay.
the so I read the book, and at the exact same line, I write the exact same thing you wrote.
Okay. Okay. All right. So, but I tried, but for a while, but then I kind of gave up. I said, like I'm going to accept it and go forward.
Yeah,
Um,
same.
but then so basically, this is like the idea here is that this is non-zero, right? So, however, so this is a biased estimator because this the bias does not equate to zero. However, you can make this estimator unbiased, and which by dividing instead of saying that instead of equation 5.36 to mention represent the bias, represent the sample variance. If you do 1 by m minus 1, right? And I think that may be the reasoning behind the difference between error and standard error, right? So where 1 is divided by m minus 1. So I'm not really sure about the reasoning, but if you do that, then you are able to. So here you can see that this was m minus 1 times m times sigma square, but this is basically flipping that. So it is essentially this one will equate to, based on assuming that this is correct, right? So if you just bring it here, this is m minus 1 time over m times sigma square, right? And so these things cancel out and you get sigma square here. So because the expectation of the sample is the same as the actual variance, this becomes unbiased, right? So that's the yeah. So that's the three examples that they talk about. And so then, so one of the other things that they talk about here, computed expectation, we can also compute the variance, and data is when do we sample the data set. Okay, so that's the variance. And so this, so they talk about the standard error here, which is no. So I was wrong. So there is a correction, right? So where they do a sample mean versus the actual mean, the sample mean is divided by n minus 1 instead. So that was what I was referring to earlier. Um, so here they talk about the importance of like being able to say that something is normal, like, right? So if you can say, you can assert to some extent that your data is follows some kind of distribution, right? Then you can also calculate confidence intervals of that distribution. So in case of a normal Gaussian distribution, you can basically compute 95% confidence intervals by saying that two standard deviations, right? So, and that becomes that this the confidence interval becomes the sample mean of the distribution minus two standard deviations, right? So that is 1.96 standard error on of that, and plus two standard deviations. So it's the space of four standard deviations around the origin. And so that is your 95% confidence interval, meaning that 95% of the predictions you would expect to see from that model would fall in this range, right? And so that is a good way of comparing pairs of algorithms and saying algorithm 1 is better than algorithm B. So it says here, if the upper bound of the 95%, so if you think of algorithm A and B being kind of side by side, and the upper bound of the error of algorithm A is less than the lower bound. So you're basically saying that you know, bound of algorithm A is less than the lower bound of algorithm B. So A is behind B. So in terms of errors, A has lower error. Even the maximum error that it has is lower than the minimum error that B makes. So the ranges, the A has a lower range of errors than B, basically. So you can make assertions of that kind of nature. And again, they use the same example where this is finding using the variance as a estimation. So calculating the variance of the sample, right? And this, so essentially, we already know that the variance can be approximated by this here. Oh, sorry, estimate, the point estimate of the distribution can be this, right? By the mean, the sample mean. So if you do the variance of the sample mean, you can. So the variance here, you want to put the variance inside now, but if you do the variance inside, this is being repeated m times. So to offset that, you have to take m, replace 1 by m with 1 by m square, and which basically, so you know that the variance for a Bernoulli is theta times 1 minus theta, and then if you just do it m times, so 1 by m theta 1 minus theta, right? So this is just yeah, trading of bias invariance to minimize mean square. So here, so we talked about overfitting and underfitting, and we talked about the cost function where the cost would have like the MSE as one of the costs and the regularization cost added to it, right? So, but they also make the point that the MSE itself is a combination of expectations, square expectation of the sample estimator minus the actual estimator squared, right? So that is so this converts into, so now we already looked at this one. So this is basically a combination of the bias and the variance, right? So based on the things that we already derived, right? So if you plot the bias, right? So the bias goes down as the capacity of the model increases, as it can see more things. It has more view into the data set, right? Either by getting more data or increasing its capacity in terms of polynomial in this case, right? Or the number of parameters. The variance will increase because it is seeing more data. So if you just think about, not in mathematical terms, but as the model capacity increases, or as it sees more data, in my case, right? So the bias would decrease. However, because it is seeing more variations, the variance would increase, right? So the bias would go down and the variance would come up. So if you look at the test error, right? So it will follow this, because the error that we already see, right? It's a combination of bias and variance. So the combination of this would be this U-shaped curve. So that gives you a way to find a place, the optimal capacity, below which the model would underfit and over which the model would overfit, right? So this in neural network terms would be governed by the number of epochs, right, of training, the data size, right? So you would be able to kind of see this kind of error and determine where to stop training, right? So that's like the bias variance trade-off that people talk about, right? So Andrew Ng's class has they talk about the bias variance trade-off, and then there is consistency. So Okay. So so consistency ensures that the bias induced by the estimator diminishes as the number of data examples grow. So this is what we were just talking about. As you see more data points, your bias goes down, right? So by definition, so the consistency here is that it's strong for almost sure convergence. Okay. So again, this is the condition. So you can see that there is like as the m is the number of data points tends to infinity, the probability, right, for it goes to zero. The probability that the difference between the predicted and the label estimates, right, the actual predicted and the actual is greater than some small number, tends to zero as m increases. So, and there is the strong consistency and the weak consistency. There is, so if you're almost sure, then it is weak. Oh, sorry, if it's um, yeah, it's weak and strong. It's just a matter of degree, and this is more like definitions that they talk about here. Okay. So finally, we come to the maximum likelihood estimation, where so the idea here is it's a principled approach to find good estimators, right? So using the idea of maximum likelihood, right? So rather than guessing that some function might make a good estimator and then analyzing the bias and variance, you would like to have a principle from which we can derive specific functions that are good estimators of different models. So again, this is somewhat theoretical. I'm not sure how it can be really applied, but so you define for a given model with in data points x and parameters theta. You can define that the optimal parameters or the trend parameters are the places where you get the best p model, right? The probability of the model for the given theta, the maximum probability. So you can do some kind of performance evaluation and say that where the best model, that theta is the model for that model. I want to use this, and because these are probabilities, they are multiplicative. So instead of multiplicative, you can this can lead to underflow because they are very small numbers and they keep going down and down. So the strategy is to take logs and sum instead, right? Instead of probability. So this is identical, right? So you'll still get the best theta at the argmax given by the sum of the log probabilities. And so here it says ex. So you can take this bit, right, of the formula and basically say that this is the expectation of the log probabilities, right? And which is basically so now you can interpret this theta, right, as a deviation between the empirical data points, empirical distribution defined by the training set, and the model distribution which is learned, right? And you can think of it as the degree of dissimilarity, which can be measured by the Kullback-Leibler divergence, scale divergence. And so the scale divergence is given by the expectation of the log P of data minus log P of model, right? However, P of data is not under your control because during training, your data training set is fixed, right? So you can only play with during training at least, you can only play with the second part, right? However, if you look between these two, right, the second part is basically the same as the equation 5.59. So there is an equivalence between the KL divergence and the maximum likelihood, right? So this is what they're talking about. So minimizing the scale divergence corresponds exactly to minimizing the cross entropy between the distributions. So this is the log, the log likelihood is basically synonymous with cross entropy, at least in this case. So it says many authors use the term cross entropy to identify the negative log likelihood of Bernoulli softmax distribution, but that is a misnomer. Any loss consisting of a negative log. So essentially he is talking about that NLL is not really the same as cross entropy in all cases, but in most cases where we use it, it kind of can be used synonymously, right? But it's not correct, right? So that's a point that it's kind of splitting hairs a little bit. So then from this point, you can now say, you can thus see maximum likelihood is an attempt to make the model distribution match the empirical distribution of p-data, right? So, and from this, you can say that, these are the same, right? So, you're trying to make these two match. So then it says that the maximum likelihood thus becomes minimization of the negative likelihood or cross entropy, or, so doing maximum likelihood estimation is the same as minimizing the NLL, right? Or the cross entropy, and which is also the same as minimizing the Kehl divergence, right? So in this sense, maximum likelihood is like a valid way of finding the best estimator. That yeah. Conditional log likelihood, and okay, let's go with this. This is I think where I was thinking about maybe. So we just talked about conditional log likelihood in sorry, we talked about MLE in this case, the maximum likelihood estimator, right? In terms of a generalized data distribution, right? But you can also think of it in terms of like a supervised learning environment where the data distribution is conditional. So you're saying that you're trying to find P of the target given the data and the model, right? In order to predict Y given X, right? So you can extend that similarly to where you say argmax of P model. You can basically say argmax of P Y given X, right? And you can do the same exact expansion that you can do you did before, and you can apply this maximum likelihood estimation as a form of optimization, right? And linear regression is maximum likelihood. Yeah, it basically just tells you the same thing again, right? Maximizing the log likelihood with respect to W yields the same estimate of the parameters W as does minimizing the mean squared error. So so this time he is basically taking linear regression and equating it with maximum likelihood, right? So here you take a normal distribution, and the conditional log likelihood of this is if you expand it with the formula, you have this m log theta, and you take the log of the normal distribution and you get these pieces and you get this part, right? But these are constants, so you don't really have much when you're optimizing these kind of fall off, right? So then you can say that this is the same as the MSE, right? So the mean squared error, right? This bit, right? So you can just divide by 1 by m, and this becomes the mean squared error. So you can equate maximum likelihood estimation to mean squared error as well. And properties of maximum likelihood, I think. So here I basically pulled these out. So they're talking about they should be consistent under appropriate conditions. So the property of consistency is that the number of training examples approaches infinity, the maximum likelihood estimate of a parameter converges to the true value of the parameter. So, and the conditions here are that the true distribution must lie within the model distribution. Otherwise, obviously you cannot recover. And the true distribution must be unique, must correspond to exactly one value of theta. Otherwise, maximum likelihood can recover correct p data, but not determine which value of theta was used for the data generating process, right? And the other piece is statistical efficiency. So it says that mean square error decreases as m increases. So there is till there is a Kramer-Rao lower bound for large m, beyond which it will not decrease further. So that dictates how efficient your model is, and that is a term called statistical efficiency. So that was the end of today's pieces. I will be out, so I have to attend a wedding next weekend. So I don't know if I'll be able to do it from the hotel room. So I'll be driving entire Friday, and then we'll attend the wedding. So I might have the time, but I'm not sure. So if I don't know how many people are here. Let's see. We are just 1, 2. Oh, you have a lot of, okay. We have 4 participants. So we can, I mean, can we skip next week? That would be very helpful for me. Otherwise,
I'll probably be out also next week. I'll be driving.
Okay. So in that case, maybe okay. So yeah. So let's. So this is the end of the thing. So we can go through questions. Okay. So so I'm looking at the chat now, and you can see my screen too, right? Yeah. So I guess the no free lunch theorem is also true for deep learning. The convolution, for example, you bias the machine learning model a certain type of operation. Yes, I think that is totally true. Yes, totally. So, yeah. When I said it was, so my point was more like you don't have to. Well, I mean, I think you're right. So I was thinking that you don't have to think about whether it's a Gaussian that generated or it's a Bernoulli that generated, right? In deep learning, you just throw data at it and it kind of figures things out. But you're right. I mean, for convolutionals, you're basically saying that there is locality, right? So you're making use of the fact that neighboring pixels are more related than further up pixels. Totally, and yeah, totally accept that. Yeah, you're good. Yeah, you're right.
I wonder how it works with transformers, like the kind of assumption you make, because you can use transformer with whatever type of data, being like images, audio, I don't know what other thing. I've seen control of robotics, trajectory, a lot of stuff you can apply your text.
I think transformers are more brute force in my opinion, right? Because they are doing attention, right? But they do attention across all elements, right? So so even if so the I think of it from the text side, right? So if you look at RNNs, right? They kind of said that okay, you have a sequence, and you get attention to all previous elements or all future elements of the sequence, and using those weights, how how much effect it will have on the current token, right? How much effect will each token have on the current token is determined by the attention that is determined across them, right? So how close they are. So and transformers kind of do it like rather than do it token by token, they do it all at once, and then they kind of go. So in a lot of ways, I think it's like a cross, or it's a hybrid of convolutional neural networks and recurrent neural networks, right? So even though it's like a sequence, you're basically treating it like one big blob, and then doing attention to figure out how much weights.
And I guess there's no go.
Yeah. So where locality is like kind of derived rather than assumed, right?
Yeah.
Well, I guess you assume some kind of sequence, whatever the type of data. I mean the inductive biases.
I think just in for images, it's like the statistical relationships between adjacent pixels, right? But for like text, for instance, then I think, or tokens, then I think it's not adjacent anymore, right? But there's like Sujit said, like there's some cross relationships that are not like obvious, but because the attention does the brute force, almost like a brute force thing that is trying to figure out, you know, these relationships between them, the statistical relationships. It will kind of capture them, right? It will give different weighting to those statistical relationships. If they don't have a lot of statistical relationship, then it's like almost like a low weighting, right? If it has more, then it's more weighting. So, but because it's doing this almost like brute force, as he's saying, that it will capture these things. So it's not just, you know, anymore like in images that is the local, very local adjacent pixel statistical relations. It's more like, well, the relationships can be stretched out, you know, in a very non-obvious way between each other, like a cross thing, as he said. So I think that's the difference between the inductive biases for both. Yeah. Or does that make sense? I don't know. Maybe I'm just rambling.
But definitely, I mean, even for neural networks, so it wasn't like completely true that neural networks, you completely ignore the data, right? So the data distribution, right? So yeah, totally. Yeah. In case of CNN, that is definitely a valid thing. Inductive bias, I don't actually know much about it. So if Barto, if you can go and, you know, if you can kind of lead this, that would be nice. These the questions that you have. What, and we can discuss, right? I mean, if,
wait, sorry, what was that? I can leave the in the Slack.
So,
or
no, here I think the keyword here is inductive bias. So is this during the bias section or?
Oh no, it's just a general word in deep learning. No, I don't even think it's in deep learning.
Oh,
it's like
I see.
In general, like in I think in machine learning, in science, there's a word that's called inductive bias. I don't fully understand. I don't remember the definition of the word, but I've seen it being used a lot. Like, for instance, when you describe this assumption that you're making on images, that they have statistical relations between them, where adjacent pixels are, you know, more related to than compared to far away pixels. This assumption that you're making, the word for it is called inductive bias.
I see. Okay.
So, but yeah, I don't remember the proper definition of inductive bias, but I've seen that word being thrown a lot around.
I see. Okay. Yeah, I didn't realize it was a continuation of this discussion. Okay, got it. Right. Okay.
Right. Yeah. It's not.
So in practice, because there's no freelance theorem, forces two different models whenever we want to solve a problem. Because once again, there is a model written better than the other, so you can't know. Yes, I think. How exactly in the loop is the validation data set used? You use training data to train the model with the training loop, but when you want to evaluate the model performance during the loop, do you also use the validation set? What exactly do you use? Where exactly you use it in the training?
Yeah, I just wanted to know in practice when you're coding it, right? I wanted to know where in the code you.
Right. So one place I have used it pretty heavily is in neural networks. So during the training loop, right, where you do the backpropagation and you do the update, you typically would do the validation at the end of either each iteration or at the end of each epoch, right? So at the end of each iteration, I think we do it at the end of each iteration. Yes.
Yeah.
So and basically we calculate the training, and at the end of it we basically wait.
Yeah. So basically, you get both the performance of the training data and the validation data, but you're just using the training data to train the model. You're not using the validation to train the model. You're just using it to validate, to like evaluate the performance of the model, right? Yeah. So but okay, so it's the end of the loop, end of the.
I think every epoch. I'm trying to remember back. So nowadays I do Gen AI, so that's like hardly
yeah, it's different, right? So, but like for smaller models, then it's. But yeah, maybe it depends. Also, you can do it at the end of epoch if you want to, but then you have to take into account then the epoch, the iterations, right?
So when you compare the training, you have to average it over the number of iterations that you had. Yeah, but I learned something here. I mean, I did not think of it as training my, or figuring out how good my hyperparameters are. I just basically used to think that, this is like almost like a mini test set, just to see how well my model does on unseen data, right? My validation set was.
Yeah.
So
exactly.
This is, so this is interesting where they think of it as like training your hyperparameters, or basically. Evaluating your hyperparameters.
Yeah, I mean, it is kind of, because once you use the data set, right, to evaluate, then you're kind of like, you have used it, right? So we can't, and the entire point with test data is that you hold it until the very end, you don't touch that, and then at the end you do it once, and then that's it.
Right. Yeah.
Here you're like, the validation, you can go back and forth, you can tinker more and more, and then it will be more than biased now towards the validation.
Validation set, yes.
Yeah.
Yeah. Okay. So how exactly in the loop? So this is the free-lunch theorem. And lately, I have also used cross-validation. So there again, also I have split it up into a validation set. So this was like an SVM for a small, because I didn't have too much data. So I did cross-validation. I split my training set into a tiny validation set, and I would calculate for each, for each of the cross-validation sets, I would calculate a validation error as well, right? And then average that over the entire set.
Yeah.
So I don't know. I mean, that's I don't know how prevalent that is in traditional neural networks, but non-neural network models, because I'm I'm doing a few of these. I haven't done a lot of those.
Yeah, me neither.
Classical machine learning is challenged by today's huge models, which I think don't increase their variance with increased capacity. Possibly. Do you have, Andrea, do you have examples of this? I don't know of. So large models, when the parameter, so I'm thinking in terms of the GenAI stuff, the LLMs, right? So as the parameters increase, right, they do tend to have better performance. But do you have like
I was thinking exactly as I was also thinking at this phenomenon, the double descent, as Barto. He put the link just a few.
Okay.
Few messages later.
Okay.
Oh yeah, there's a really nice graph in that one. I don't know if you can. Yeah, this was 2019, so mind you, it was like 5 years ago.
Okay.
But you can see there, you have the U curve as indicated by the theorem. But then if you continue to train, or continue to
it keeps falling,
expand
right?
the capacity, model capacity, it seems to have a second descent. That's why hence the name double descent, which is even lower error than the first descent.
I see. Okay. Cool. This is good. Thank you. I didn't know that.
But the thing is, this is like a weird phenomenon. I haven't seen the researchers talking about this too much, so I'm wondering if it's like very limited then to the problem or something. But yeah, if you scroll down even further, you can see they elaborate. Yeah, there exactly the critical regime, the interpolation threshold. The idea is something like I don't remember. Something with high dimensionality, and when you work with high dimensionalities, data becomes very sparse there. But if you have a very strong model, you can you can somewhat like increase the model expressiveness by making it will be better at like interpolating between the points or something, even though the data is very sparse in high dimensions. I don't know. I don't remember really. But that's where the interpolation. That's why they're using interpolation.
Okay.
Or...
Yeah, I actually there was this one time I participated in a LLM, for the Indian language, create fine tuning an LLM for an Indian language, and I was just a drone, right? So I would they basically recruited me to run their thing on Colab. It's distributed training, so I would do their on Kaggle and Colab. So basically, they needed free GPUs from different all over the world. So I was one of them, but I was surprised. They kept grinding, and at this, and we would get like really low numbers, like but it kept going down, and so I'm thinking that this might have been this region, right, where they were going down. I didn't realize it at that time, so this to go back and look now.
Yeah, I mean, like at some point it goes down first as according to the theorem, but then it goes up, but then it goes down again, and that's the second descent.
Right.
But yeah, that's so that maybe explains why some things, people, you've seen the graphs, right, of people training things, and they're like, oh,
Right.
it keeps going down, but then suddenly it goes up, and then it goes up, and then suddenly it goes down again.
It
Like,
keeps
why
going
is
down.
that?
Yeah.
And this might be one of the phenomenon that they are describing here. But the problem is I don't see this being addressed a lot by researchers in general. So I'm wondering if this is like very limited. As I said, like it doesn't occur maybe that much in nature, in the wild. I don't know.
I think it does occur, and it's a known phenomenon. But I think the issue is we don't have a theory about why.
Yeah.
But you were saying something about that. If you find again the reference, I'm interested in it.
There has been one thing that sounds similar to this, which is called grokking, and I haven't read about grokking, but that seems to be like the modern version of this. Maybe, I don't know. I haven't read grokking, so I don't know the nuance between double descent and grokking, but they kind of feel the same. But I don't know.
We can find out, right?
Yeah, or you can ask LNM about that or something.
Yeah.
Grokking. What's the difference between double descent and grokking? If there is any, but yeah, I guess you guys have heard about grokking at least. It's
yes.
Like people have been talking about grokking in terms of LLM, maybe, I think. But I haven't read anything about grokking.
I've heard about it, but I actually don't know what it is.
Okay, two distinct phenomena.
Change of regime.
Yeah.
And you have this kind of double stairs of it seems to be flat and plateau, and at some point, the error goes down.
Again. Yeah.
Cool. All right.
Yeah. So yeah, I mean, so at least there seems to be more research on grokking at least nowadays.
Right.
And people don't talk about the word double descent.
Yeah. Okay.
They seem to have some similarity. But I don't know. Yeah. Did anyone have any more like questions about this chapter in particular? Because I don't. I haven't read like I'm trying to catch up. I joined pretty late.
Right. Yeah. I mean, I think I have to go back, and I missed 2 weeks. So I have to also catch up on the probability stuff.
Yeah, I'm also a little behind on the 4th chapter. So yeah, that's the chapter I missed. So I have to catch up on that as well.
Yeah. I think the 4th chapter is the so far most demanding, maybe.
Right.
Like theory.
Okay. Right.
Like it's only like 11 pages or something. Well, it's like 17 or something, but yeah.
But
there are
I
a lot of
feel
things
like it's packed with a lot of information in those 11.
Yeah, like you can have one little sentence that's very short, but that little sentence has a lot of like unpacking to do.
Okay.
For instance, I did in the Slack channel recently ask one question which Amit actually answered, which was really good answer. Yeah, that one was like, it was only mentioned in one little sentence, but like it took a while to like unpack that thing. I even asked, like I tried asking LLM, you know, ChatGPT and didn't even know. It gave me the wrong answer. So yeah.
All right. In case if we don't have anything else, then we can give everybody else like half an hour back, right? Say 20 now. So,
yeah. And Sujit,
yes.
so about next session, is it there next Saturday, or we are taking a break next Saturday?
I would prefer we took a break. I don't know if I can do it from the hotel room.
Okay, sure. So maybe, yeah, let's take a break next Saturday and come back.
Right.
Yeah, next week. Yeah.
The week after, I'll finish off the rest of. There's about 6 sections here, so that would be the end of chapter 5.
Sounds good.
Yep.
Okay. Yeah.
Okay.
I don't have any questions either.
Yeah. All right. In that case, I'll stop sharing, and then we'll see each other next week.
Yeah.
Yes.
All right.
Bye bye,
Okay.
everyone.
Thank
All right.
you.
Bye. All right. Thank you. Yeah.
Bye. Thanks.
Bye.